I know that's a bit late, but remember, this is the biggest, shortest, most technical LLM conference in the world so far. So I think we're doing a good job. Once again, I'm Alexy Khrabrov. I'm one of the co-organizers of this. I'm the only local organizer. I run Bay Area AI, the oldest technical AI meetup, started as NLP meetup, maybe already 10 years. Join us, bay.area.ai, and also run the conference called Scale by the Bay. It's in this 10th year, it's the technical conference about software engineering, cloud architectures, and data pipelines for AI and ML. So we care about AI at scale, right? We don't care about AI in one notebook. We care about it at web scale, and we're going to have it back in November. So scale.bythebay.ai, that's our conference. And also in other life, I am director of open source science at IBM. We connect researchers and open source developers to accelerate science. So this panel is about performance, right? And there is a lot of meanings of performance. There is performance of models themselves. There is performance of the results. There is performance of LLMs as benchmarks. There are performance of LLMs in enterprise deployments. So we'll kind of tackle all of this in different ways. First, let's our panelists introduce themselves. Begin with Chip, and I'll hold the llama for you.
But why can't I have it?
I'll tell you. This is going to be a mechanism of moderation. I'll let you know in a minute, but for now you can have it.
Hey, my name is Chip. So we actually have an alpaca farm. So yeah, so we have like about 22 of those. And they're very cute. But it's not my full-time job, unfortunately. So for my full-time job, I work for Claypot AI, which is unified data for real-time machine learning. And of course today, so we have to mention AI. So yeah, for real-time machine learning and AI.
Oh, no worries. Thanks, Chip. I'm Greg. I don't have a llama farm, but I went to a llama farm recently. It's called Alpacas by the Sea. It's in Pacifica. It's absolutely wonderful. It's like the best thing you could possibly imagine. My day job, I'm CTO of Lamini. We're language models on your private data. So we help you take an existing language model and then specialize it and then deploy it on your private data.
David Kanter, I'm the one of the founders and the executive director of MLCommons. Our mission is to make ML better for everyone, and we do that through benchmarks and data sets. Greg actually helped lead create one of our best data sets, which is a 3 terabyte speech recognition data set. But since this is an LLM conference, I'm going to tease you all by saying we have a GPT-3 speed benchmark to see who can train GPT-3 the fastest with their systems. And unfortunately, the results are secret until 9 a.m. tomorrow morning. So stay tuned.
Wow, that's tough to top that. Yeah, so my name's Ankit. I work on model serving at Databricks, particularly on GPUs, and these days, a lot on large language models. So yeah, I'm super excited to chat with you all today. By the way, I was told there was going to be a llama, but I thought it might be a real one. It's just like a... Yeah. Thanks.
The llama's like the talking stick from 3rd grade. You can
Perfect.
only talk if you have the llama. It's like a lock.
Well, there you go.
Oh, okay. Hey everyone, my name is Beyang. I'm the CTO and co-founder of a company called Sourcegraph. Some of you might be familiar with the code search engine that we built. It's a search engine for code, helps developers understand large code bases. But the reason I'm here is we recently built a coding AI assistant called Cody that makes use of some of the underlying abilities of Sourcegraph. So it uses code search and code intelligence APIs to essentially fetch contextual snippets that then are fed into a large language model. So we're doing kind of like the in-context learning. We're using a variety of large language models underneath the hood to build this tool and kind of integrating it with classical developer tools in a variety of ways.
Thank you, Ben. Maybe I may have my llama back. I will explain in a minute why. So we actually try to bring llamas here, right? And so if you remember, in March, we had the biggest AI meetup in the world called Woodstock AI. So as a local Bay Area organizer, I was the co-organizer of Hugging Face of Clement Lang. So we brought llamas to the Exploratory. We tried to bring them here. What happened is, in the city of San Francisco, you cannot have live animals because 100 years ago, Ringling Brothers Circus, animals escaped and they bitten people and they stomped on them. So in the city of San Francisco, you cannot have llamas. Why? You can have them at Exploratorium. It turns out it's under Port Authority. So next time we'll have a llama event with live llamas, we'll do it there. All right, for now, how am I going to use this? So this is a new experimental device. So if we have a very tight panel, so if one of the panelists is going on and going on, the llama is going to snooze like this. All right, maybe not, we'll see. I don't want it to be like the main thing. All right, so performance. Let's do the following. Everybody, please define performance of LLMs as it really matters to you. What is your definition of performance? And we'll start with Chip.
I regret sitting here. For me, performance, I think there's like, so I think for me, I think there's only three things we'll care about: accuracy, latency, and cost. And that's what performance means to me, like how to like optimize for the three key metrics. Like whichever works for you, like sometimes maybe like, okay, is this, okay, I'm very nervous watching.
No, it's nodding,
this.
okay. It's approving.
Yeah. So optimize the three metrics. Like for some use cases, like you might be like okay with like being like things a bit slow, so you want to optimize for like being cheap and correct. But like if it's not, sometimes you need like exact latency. Then you might need to sacrifice either correctness or cost.
It was a good start. Let's see, performance. So many different aspects of it. I think one thing that I see people running into a lot related to performance is I just don't have a big enough GPU, or I don't have enough GPUs to run my language model. That if you want to take, let's say one of the open, llama-based language models, maybe it's 20 billion parameters, 10 billion parameters, you probably need a pretty recent GPU, like an A100. And those things are really in short supply. So I see a lot of people just blocked on memory capacity of just not being able to run language models.
So I think Chip had an excellent definition. I'm going to have to add on to it. I would say time to solution for training is a performance metric you might care about. And then in terms of accuracy, right, like one of the things that's obviously a lot of people pay attention to these days are things like robustness, and many of the AI safety related concerns, hopefully the community will be able to boil down to some sort of performance metric. That was an awesome definition, Chip.
Yeah, I've got to say the same thing. I think Chip's definition was great. I'd love to add robustness to it. I think for me, performance is about value. You've got a lot of different options out there, small models, big models, proprietary models, and really, when you think about running one of those models, you might optimize it for batch or latency, and that's about what value means to you in your application. If you're running an application where it's really, really critical someone sees the answer immediately, value means you need the absolute lowest latency. But if you're running something where it maybe doesn't matter as much, then value means I need to have as few GPUs that I'm running this on as possible. So maybe you want as much concurrency as you can get. Kind of speaking a little bit more to what Chip was saying actually, right? Like there's a bunch of different variables to optimize.
Yeah, so for us, it's quality, latency, cost. So basically what Chip said. And also piggybacking what Ankit was saying, I think the weighting of those three factors differs depending on the use case. So for something like code generation, that's a case where we actually find that a cheaper, faster model that's stupider works better because you don't want to be sitting there waiting multiple seconds for your code completion. But for something like Q&A, when you're asking a question, you can tolerate a little bit longer latency, although even there, we think that there's a trade-off. So, like GPT-4, I think is the best model in terms of quality of the output, but we find that, at least for our use case, the latency that you spend waiting for an answer can sometimes be, it's not the right trade-off for a use case where you're just asking questions about a particular code base.
Can I add actually one comment? So actually specifically for inference, like to drill in on latency a little bit, like I think one issue is there's different levels of sensitivity. Like you can talk about latency in terms of averages, you can talk about it as like P50, P99, right? And so there's going to be some applications where it's that absolute tail latency that matter, right? And then there's going to be some applications where average latency matters, and then there's some things where you're batch processing and you're like, oh, latency, what's that? Right, and then it's, as you say, how do you use as few resources as possible?
Right, and actually, like, speaking to that, right, latency in terms of P99, P50 is super important to reason about, and it's hard for LLMs because your latency scales with how long that thing wants to keep talking. And so I think that's actually a really cool opportunity for co-design between training models and serving them, because you kind of want your model to be concise. And that's why people have done work on like telling GPT-3 to be less wordy and things like that, or more wordy if they need it. But that is an important factor in how much you're spending.
I think I just say to jump on that. Do you think there's like cultural difference in like how people prefer like longer or shorter, or like depending on the use case, whether they prefer longer or shorter responses?
Yeah, I think it's on the use case. So like for summarization, you probably don't want it to ramble on too much, because then it's not summarizing. But if you're brainstorming, then you certainly want to get as many thoughts out there as possible.
So I had a very interesting experience in Washington, D.C. recently, and I was meeting with a bunch of lawyers. And I was talking to one of the lawyers, and I said, you know, one of the things I've noticed is that in law journal articles, people perceive quality is linearly correlated with the length of the article. Is that true? And the woman said, oh yeah, that's absolutely true. Long papers are good. And I'm like, have you ever met a technologist? Because like, we prefer bullet points, you know, not long papers. Like, you know, some of the most impactful papers, like you think about like Shannon's information theorem, like those might be single-digit pages. And so I think it's not just like the context, but also the people you're interacting with, right? If you're trying to write your college essay, you probably have a particular page target in mind. But yeah, I think in general, like shorter outputs are probably better, but then maybe you want a really big context window up front to scan over.
Do you wish you had a stop generating button for lawyers at times? Just kidding.
I have an embarrassing story. I've only actually used an LLM like maybe a handful of times.
Just while we're talking about generation, just a quick performance tip. The cost of generating tokens is actually higher than the cost of the context, like the input to the model. So every token that you're generating, because the model has to read in all of the weights to generate every subsequent token, it's actually more expensive to do that generation than it is to process a long document.
Thank you. I think we touched on a lot of points, and also I really like, you know, you guys, you should have a conversation, right? Like it shouldn't be just like me asking questions, you answer. So, and we'll reserve the time for audience questions in the end. So please think of your questions, right? We'll have probably about 10 minutes in the end. So I want to piggyback on what Ankit said, right? So inference versus training, right? And actually, let's kind of explore. So I talked to Demetrius, right? He runs one of the biggest communities, MLOps community, and he did an online conference on LLMs. And I asked him, like, what questions did come up, right? What trade-offs people see? And so here's some, right? So in performance, it is fine-tuning versus information retrieval versus large context window, right? Obviously, that's, I think we have kind of advances in all of these three areas, right? Then there is a question, you know, small models versus large models. Do you have to have a large model? Obviously, a large model maybe have more parameters, but obviously it's harder to run, harder to use for inference, harder to train, and for value, right? Like you said, for your metric of performance, do you really need this? Maybe the overall value given the cost and the size is lower. So I want you guys to talk about like your opinions on the architectural features of models for performance in any order.
Well, I think Greg, you know, made a great point, right? Which was that the input context is less expensive than the output generation, right? So to that point, if you're practically trying to build an LLM application right now, your best lever is to toss as much relevant input context as you can, as the model will let you, and see hopefully that it comes up with a good answer. And you know, smaller models will do worse with that. Bigger models will probably do better with that, at least in what I've seen. But I don't know what others have.
So I think there is kind of this like step function thing that happens that we found, like, so generally we like to optimize for lower latency because for end user use cases like code Q&A and code generation, the latency matters a lot. But when we're answering kind of like a high level question that the user's asking about the code, we do need a model that at the very least has this kind of chain of thought ability, the ability to kind of like synthesize multiple pieces of context into a coherent answer. There's some models that are like too small to do that, and in that case, like if you try to do the context stuffing approach that you just described, it can be not good for the end user, despite the model being cheap.
So the latency point's really interesting. It's actually really interesting, like, why we're all here. We're all here because we have these giant models. Like, we're here because we have GPT-3 and GPT-4, and the performance of these things is really amazing. I think actually everybody's been using language models that are low latency for a long time. If you've ever used like spell check in like Microsoft Office from like 1990, it was a language model and it was super fast. It was just not interesting, like not interesting at all in the same way that like GPT-3 and GPT-4 are. So I think one of the most interesting things actually about performance with regard to language models is that we're on this trajectory that takes us from the Microsoft Office spell check to GPT-3, GPT-4, and that it keeps going. We actually understand some of the theoretical like reasons why these models are learning, and they just keep going. So I think one of the most exciting things for me is that these are the worst models. Like, as good as they are, these are the worst models we're going to see in the next decade.
I mean, I think one of the other things that's interesting, and just for context, Greg and I helped define ML-perf inference, and one of the things there is you have a bunch of people competing on how fast can you make inference, and there's like so many techniques, and I get the impression that when we look at the high end of these models, like, you know, we don't know what most proprietary models are being deployed on, right? Whether it's BARD, GPT-4, or whatnot. But it's super common that you can trade off a very small amount of accuracy for an order of magnitude or more reduction in compute and potentially in memory footprint, right? Like, it's very normal to be using a 16-bit floating point or 8-bit floating point, although we don't have a standard for that yet, and there are people who are looking at, you know, 4-bit either float or int, right? And so each of those, you know, gives you sometimes a factor of 2, sometimes a little bit more, but there's like hard systems engineering that goes into that, or, you know, dynamic batching and other things. And so, like, one of the things that I'm super curious about is actually how many of those techniques from sort of system optimization have been thrown at inference for these large language models. I suspect it's not a lot because I don't think there's really, you know, sort of a push button flow yet for any of this.
Yeah, so, you know, that's, you know, to plug myself a little bit, that's what we're trying to build at Databricks. I think that we're still super early, both from the research point of view and the systems point of view. As a former systems person myself, I think there are cool adaptive batching type of techniques that people have tried, but I don't think people have gone very far or deep in terms of how they're doing those. If you actually look at how these models are executing on multiple GPUs, those are traditional systems approaches to doing matrix multiplication. So if you studied matrix multiplication in 2010, a lot of those same techniques are being applied just in these large language model libraries. But, you know, speaking to the points around 4-bit, 8-bit, I think it's such an exciting direction because it almost speaks to, and, you know, it's not scientific to say this, but it almost speaks to, like, maybe there's some level of understanding that's being achieved in these weights that isn't, you know, super granular due to, like, particular weights that exist. And I think it's really early days on how people are going to build these models. Like, I think GPT 3.5 Turbo, for example, is a distilled, I mean, the rumor is that it's a distilled version of a much larger model. And that could be a really exciting direction that the open source community goes.
Do you want to define distillation for folks who may not know?
Sure, yeah, like maybe a quick explainer is just that distillation is the process of taking a much larger model and almost having it teach or train a much smaller model so that you can kind of take some of the insights that larger model has and hopefully try to bake that into a smaller model. And that's like a 10,000-foot view on distillation. There's a lot of really deep work here, but that's kind of what it is.
So I think, like, can I ask you guys, like, I want to hear questions about, so, like, just still, like, a lot of techniques, a lot of things to, like, discover and optimize for inference, right? But who would be, like, the good people to do so, who can capture the opportunity? Because, like, do they have to work for big research labs to work to such this big model, or anyone can just spin up, like, a random model at home and, like, experiment with those?
I think the rise of open source has been really interesting recently. I think, as you know, others have alluded to here, there has been this space of technologies like low precision training, low precision inference, And there's been this rapid innovation, so there's this pool of different technologies. One of the really interesting recent technologies was released by DeepMind. It was called Chinchilla. So this was actually an adjustment of the size of models that used to be way too big to fit on anybody's machine, like any real like hobbyist, like your laptop. Chinchilla adjusted the appropriate size of models down by about 20 times. So it finally got down to the point where you actually could run it on a workstation, you could run it on a cloud computer. And this has actually enabled open source developers to release many iterations on top of that, to start including some of these optimizations like low-level C++ optimizations like mixed 4-bit and then higher precision 32-bit inference engines. So I actually do think that there's a thriving hobbyist community or open source community that's been relatively recent, like even within the last 6 months.
Yeah, I plus one to that. I think there's still a gap between where proprietary model inference stacks are and where the open source stacks are, frankly. If you look at these larger GPT-4 style models, people are using very advanced techniques like mixture of experts that, frankly, no one has done a good job of in the open source community yet. But if you look at things like GGML and faster transformers, there's really, really vibrant communities. And I think it really originates from hobbyists, and they're moving really fast. So I think it's quickly kind of coming together as open source tends to do.
It also depends on the use case, right? So like if you're looking for a language model from which you want to extract embeddings for something like information retrieval, where you do the thing where you compare the the distance between two text documents in the embedding space of the model, those models tend to be super small, and you can optimize the heck out of them. And actually, it's what we found is you can get a much better model for information retrieval by taking an open source model and fine tuning it than you can get from any of the proprietary APIs. For code generation, that's an application where we think the open source models are basically on par with the proprietary models that are available right now, because again, these are typically smaller, faster, but dumber models. I think the kind of remaining frontier at this point is kind of the more chat-based, logical reasoning models, where I don't think that there's any open source model in existence unless, you all know of one that comes close to GPT-4 in terms of reasoning ability.
I think GPT-4 still wins, but the open models are getting close. Like the Manicore, Falcon, family of models are at about Google Bard level of performance, which is amazingly good if you imagine compare that to what we had about a year ago.
So as a hardcore systems guy though, I mean, sort of one of the points is, given Moore's law, given advances in algorithms, all of these things, right? If you want to skate to where the puck is, 1 trillion parameters seems really hard today. I sincerely hope that within my lifetime we'll be doing that on our phones with milliseconds of latency, right? And so that's kind of we should be thinking about that. I think Greg's point about, Microsoft Word has an embedded language model that runs every single time you type a character. Right, imagine a world where that model is comparable to GPT-4.
Do you think there will be a Moore's law for inference speed?
Okay, so I have some kind of nonconformist views. Moore's law is a little over 50 years old. Is there anyone in the room who's over 50 years old? Please raise your hand. This is not a discrimination thing, but so you guys are all still alive. You're looking pretty healthy. But you might not be quite as fast as you were when you were 20. And that's kind of how Moore's law is doing. I have a lot of friends who work on device physics, and there's a tremendous amount of investment to make sure that the next generation process technologies will be faster. And the other thing is, a lot of companies have just phenomenally talented architects. And one of the things to me that's really beautiful about ML is it is a full stack optimization problem. Right, you can optimize the data, right? So there was a great demonstration by GraphCore that if you sort your tokens into similar lengths, you can get about a factor of 2x speed up in training, and now everyone does that in MLPerf, right? That's just purely a data manipulation trick, right? You can use faster training algorithms, you can use better FFT libraries, better compilers, better chips, larger systems, faster silicon. So we've got a huge number of tools, and as long as there's this promise out here, sort of the job of the industry whether you're purely at a software company like Databricks or an ML-focused company like, how do I pronounce your company name? Lamini, right, is, yeah, go with the llamas, right, but or you're a silicon company, is like, how many of those tricks can we throw to add a lot of value?
Thank you. So I think now I'll ask one more question, right? And then we'll ask audience questions. So I think Beyang actually asked this in our prep, right? Let's kind of ask how this performance relate to architecture. So I think you mentioned search, right? So the results, right, what we care about, mostly currently done with prompt engineering, but there is actually interesting emerging ways to interact with LLMs, which are not prompts, such as the DSP framework from Stanford, demonstrate, search, predict, where you give examples of what you want, then you define the search space, right? And then the thing goes and finds, and then it predicts what you want. And I think with OpenAI functions, we see a similar way, right? So you give data sources. So I wonder, and that determines both the performance as a result, but then also architectural. So I wonder, what do you guys think, our current ways to interact with LLMs affects the performance as we define it? Where can it change if we change the ways we interact with LLMs? Obviously, like in the future, maybe with your phone, you're not going to spell everything. Maybe you're going to show it, right? I wonder if you guys have thoughts, and obviously Beyang, you have experience with this. Maybe you can start with what you mean by this with Cody.
Yeah, so just for the context, the way Cody works is we essentially, when the user asks a question like, hey, how does this project work? Or maybe like write some code that shows me how to use this API. What we do is we issue a bunch of code searches and kind of like code intelligence requests, like find references and go to definition, to pull relevant snippets, sort of mimicking the way that like a human might go about understanding a code base. And then we place all those snippets into the context window of the model, and then we ask the user a question. So this is just an example of what some people call in-context learning. It's also called retrieval augmented, retrieval augmentation. And so essentially what we're doing is composing the language model with other systems. And so now the overall performance of the system is not just the language model latency, but sort of like the added latency of this back and forth that happens between the language model and these other systems. And if you take that to the next level, I think what a lot of people are starting to do is play around with like agents, where like you basically have a language model and you say, here are a set of tools or APIs that you can access. Here are a bunch of examples of how to use that. OpenAI functions, here's a templated set of functions that you can invoke to fetch additional information that you might need to answer the user's question. So it makes it a very multivariate question, this question of performance.
Yeah, I mean, I think retrieval augmentation is super popular these days because current large language models are pretty bad at telling you the truth if they don't know the answer. And so that, I think, is in some ways papered over by kind of asking it to think a couple of times about the different hops, right? As the DSP paper does, it basically gives this example of someone, for the audience generally, where you might ask the language model a multi-hop question, and the language model would then like maybe be asked a couple of times, like, hey, what is, if I'm asking how many stories a castle has, which castle is it, right? And then maybe it uses that to generate a better response. I think accuracy is going to be super important for a lot of use cases. And so the trade-off is probably worth it for those. But for others, maybe it's less worth it, like summarization, for example.
Right now, at least with the agent stuff too, like the accuracy kind of degrades over time because like every step along the way is a chance for it to mess up. So if you look like compounding, the rate of an error kind of goes to 1 the longer your chain of reasoning is. And it's also super slow. So like I think, I don't know, like one question for kind of the folks working at the lower levels, like, do you think we'll see performance improvements in the next like year or so that will actually make these multi-step workflows more tenable from an end user point of view? And maybe like, will we see like models that are specifically geared towards this like agential kind of like tool use?
I think we will see specialized models. I think one of the best examples of specialized models is the move from GPT-3 to ChatGPT, where GPT-3 is trained just on the internet data, like imagine just a stream of Reddit comments or so on. You may get what you want, you may not get what you want, but if you just take a small amount of data, like maybe 50,000 examples of questions and answers, and then fine-tune the model on that, it can actually generate like a much more coherent, like just better suited for the task of question answering responses. And so I think we'll see the same thing, or there's the potential to see the same thing for tools of actually taking models and then specializing them so that they don't just, do what they would do with a random Redditor would do with one of these tools, but they're actually proficient in using the tool.
So one of the observations I'd make is that, we've been developing software for a really long time, and we have a lot of tools and principles that we sort of operate by, right? Composability is one, introspectability. And so one of the things that's very interesting is in the ML world, a lot of these things have not yet titrated in, right? There's no GitHub for data, right? There should be, right? Can you imagine? So some of us did develop software pre-GitHub, and it was painful, right? But so all of those tools that we have in software, there are analogs in the ML world. And so the question in some sense is, okay, now that we have the ability to compose, what does that mean? And I think, Greg, you hit the nail on the head, which is we're going to see specialization. The ideal system, like for Sourcegraph, I don't know, but I would speculate you probably want an array of models with different latency, right, and different trade-offs. And there's going to be a curve of, sort of accuracy versus performance, and you're going to want to select the right one or the right ensemble of ones.
We have 3 models actually right now.
Right. Yeah, and so the question is there a future in which maybe you want 7? And then the bigger question for the whole industry is how do you shift all of those curves in the right direction? And, I think as we get more advanced tools, we'll sort of see a lot more specialization, whether it's on the latency axis or, what if you had a model that was specialized C++ only and one Python only?
Thank you, David. So we have 5 minutes for questions. Maybe one of the guys can give up the mic for the audience and share with others. Thank you, David. Jasmine, please raise your hand, and Jasmine will bring you the mic for audience questions.
Sure. How do you see the, I guess, are there any models that are worth kind of fabbing onto a chip, getting a foundry to create a processor for, and how do you see RISC-V as fitting into that? And I guess, do you think that's going to slow down model development?
God, I'm the silicon guy. Okay. So I'm going to just paraphrase the question. Is it possible to take a specific model and make a chip that is hyper-optimized for that model alone? So it is possible to do that. You would probably get enormous performance gains, and then you would have to retrain the model, and you'd be in trouble, and you would have a very expensive piece of silicon that's no longer worthwhile. There is a constant trade-off between sort of the general purpose nature of silicon and specialization. If you look at every chip that is out there, they are all general purpose to the extent that certainly they can run a family of models. There are some that are optimized, for instance, for inference using attention. I know of at least one family of chips like that. But that's really, it's a complex economic trade-off. And the other thing to keep in mind is, building a cutting-edge chip is pretty expensive, and so oftentimes you want to amortize that over a large market, which means multiple flavors of models.
Just a really quick one. I thought that's what NVIDIA did. I thought they built a GPU that was just really great at running transformers, and that's what's powering all of our language models.
So I think even before you go into designing chips, there's an intermediate layer, right, like compiler. I think that's a space that I think it took a while, right? There's always people optimize, run ResNet or GPU. I think people optimize for how to run GPT models on GPU.
Right, and it's part of that same trade-off, right? You can go all the way deep and write code that runs exactly one model and it'll be super optimized, or you can go the compiler route and it will be less good probably. I think it's probably too early to make a chip for something, because even if you look at the software stack, a new model like Falcon comes out, it has a slightly different attention mechanism, and all of a sudden you're out of luck, and that's a tough situation to be in.
I think like also like on top of that, I think like transformer is very, very sticky architecture, but we do not know how long it's gonna last. And another point, I think like a lot of now today people are tuning, so I have a little beef with like the way people say like 100 billion parameter, because like there's a whole world of like dense versus a sparse model. And when I think like a lot of people are arguing a dense model, but I do think there's a lot of promise in sparse model. And when we reach that point, like number of parameter doesn't mean much anymore.
So actually, I mean, like a really interesting open question that I'm not sure I have an answer to, but is, you know, when we started working on MLPerf, you know, call it 5 years ago, transformers and attention were sort of coming into their own and were replacing RNNs. Will we be using attention as the basis of most of our ML 5 years from now? I have no idea.
It's very hard to predict, and like related to sparsity, I am a believer in sparsity in the long term. One of the things I feel like we haven't cracked it though. I feel like we haven't figured it out yet. I know right now there are more than 5,000 research papers that are written about different sparsity methods, but our state-of-the-art models that we use do not actually use sparsity.
I think we have time for one more question.
Hello. So I was wondering, you have been talking a lot about inference and the performance in inference, but how important is the performance in model training or fine-tuning? Is something you are concerned? You spend a lot of time, money on it, or what do you see in the industry?
So there was a great paper from David Patterson at Google. And so for those who don't know, he's sort of one of the fathers of modern computer architecture. And he talked about the balance of training and inference at Google. And training is about maybe a third of their workload, and inference is about 2/3. More generally, if you just step back, you know, training is similar to compiling code. It matters a lot to developers, but realistically for most people, no one cares about the speed of compiling code. What matters is the speed of running that code. In the long run, inference will dominate training.
What I will say though is that if you are optimizing training and you're training a massive model, if you're doing a huge pre-training job, you may literally not be able to get the GPUs you need to do your pre-training job if you're not doing a good job optimizing your training stack. So I think it's actually quite critical to have a really good optimized training stack.
Jensen always says, the more you buy, the more you save.
Thank you. I think we've come to a close. I just want, you know, each of you to kind of leave us with some parting thoughts. In your own work, where do you focus on performance, right? Where do you immediately kind of think of performance as you implement LLMs?
Latency for sure. We are all in with like how to make things run faster.
I mean, I think it's quality. It's got to be, the end application has to actually work, and you have to get it to that point before you can focus on the other pieces.
I'm greedy. I want high quality, low latency, and then I want to run it on an embedded device that sucks down like 5 milliwatts.
Yeah, it's not just you actually.
I also want a magic lamp and like 5 wishes.
I would say in an ideal world, all 3 of those, but I think in the long run, concurrency will be the hardest thing for people to get right. And figuring out a way to keep concurrency high but latency low is tough.
Cool. So I'm coming at it from the application level. So the ultimate performance metric for us is developer time saved. So it's like how much time can we save our users, the developers who are creating the software that powers the world. So to the extent that we can make all this stuff like way faster, performance is, or I should say speed, latency is a really key feature.
Thank you, everybody. Let's thank all the panelists.